Hello viewers, welcome back to my channel. Hope you are doing great. If you haven't subscribed to my channel yet, please go ahead and subscribe. I have created several playlists for this channel to cover various categories of problems like BFS, DFS, dynamic programming, binary search, union find, and so on. So please check them out as well. I have uploaded the code for this problem to GitHub repository. You can get the link from the description below this video so that you can follow along. Let's jump into today's problem. Check completeness of a binary tree. Given a binary tree, determine if it is a complete binary tree. So the definition from the Wikipedia, the completeness binary tree, right? Complete binary tree. So in a complete binary tree, every level except the possibly the last is completely filled, and all nodes in the last level are as far left as possible. It can have between 1 and 2 power h nodes inclusive at the last level h. So basically we are given the definition of a complete binary tree. So what is that? It can have some h levels, and except the last level, all other levels should have all possible nodes, and in the last level it could have possible level number nodes, all 2 power h nodes, but it can have less number also, but all nodes in the last level should be as far left as possible. So that is what is the definition. So if you go ahead and look at the example 1, right? So 1, 2, 3, 4, 5, 6, this has 6 nodes, and the level 0, that is the root node. So if it has a root node, then it will be just a root node. And in level 1, there are only 2 possible nodes, and level 2, there are 4 possible nodes, but there are only 3 available, but those 3 are left as possible, right? So that's the reason why this will be called as complete binary tree. Whereas if you go look at the left second example, right? So it has also 6 nodes, but the level 0 has 1 node, level 1 it has 2 nodes, that's good, but level 3, even though it has 3 nodes, there is a empty node. After 4, 5, the left subtree of 3 is empty, whereas right subtree it has a node. So this will not be called as complete binary tree, because by definition what it is, all nodes in the last level are as far left as possible, right? So in the example 2, 7 is not as far left as possible, right? Because there is an empty left subtree for number 3, which makes this example 2, the tree in the example 2 is not a complete binary tree, right? So let's try to understand in a bit more, right? So let's say a tree has h levels, right? It doesn't matter how many levels it is, I'm calling it as h levels. So for the first h minus level, all the nodes should be present, right? All nodes should be present. So that means each level L has 2 power L nodes. So level 0 has 1 node, level 1 has 2 nodes, level 2 has 4 nodes, level 3 has 8 nodes, and so on, right? So 2 power L number of nodes are there in each level, right? But the final level, that is we call as hth level, it can have 1 to 2 power h, right? It can have 1 to 2 power h nodes, but whatever the nodes that are available, they should be as left as possible. That is the constraint, right? So like in example 1 that we saw. So how we are going to solve this problem is, we are going to number the binary tree nodes, okay? So the numbering of the binary tree node. So I would like to present with an example how we are going to number the binary tree nodes, okay? So if the node is numbered I, so remember, just want to remind, this I is not the value Okay, there is something called value in the binary tree node, right? So in the example 1, the value at the root is 1, value at the left subtree of the root is 2, value of the right subtree is 3. So I am not referring to this value, but this I is separate number that I want to put a number to each of these. So in some cases, like example 1, the value and number are actually same, okay, but this numbering is different from the value that is present inside the binary tree node. Okay, so imagine there is some numbering is happening. Okay, so if a node's number is I, right, so what will be its left subtree's number and what will be its right subtree's number? That is what we are going to see. So its left subtree's number will be 2 into I, right, 2 times that of I, and right subtree is 2 times that of I plus 1, right. So that is what we are going to number. Okay, so node, if it is numbered as I, the left subtree will be 2 into I, and right subtree is 2 times of that of I plus 1. And by following this principle, right, number I and left subtree is 2I, right subtree is 2I plus 1, right, we follow that principle and let's construct a binary tree for only this numbered binary tree, right. So our root, we will start with 1. Okay, so I is equal to 1, right. So that's what it is. So if I is equal to 1, as per the principle, left subtree will be 2 into I, right. So that will be 2 into I. What is I? 1. So 2 into I is 2. Okay, and what is I? Right subtree? 2I plus 1. 2 into I plus 1. 2 into 1 plus 1. That means 3. Okay, so that is what is the right subtree. So let's go further along. So here 4, right. So what is I here? 2. 2 into 2 is 4. 2 into 2 plus 1 is 5. 2 into 3 is 6. 2 into 3 plus 1 is 7. So likewise, we have built this numbered binary tree. Okay, this is a numbered binary tree. So what we are going to use is, we are going to number each of these nodes in the binary tree. Okay, so we are going to number each binary tree node. So once we number them, right, we will use a BFS, that is breadth first search traversal. So breadth first search traversal we are going to use, and we see if any IDs are missing in between. Like in the example 1, there is nothing missing, but if you see example 2, 6 is missing, it has to be 6, so this position is missing. So since that is missing, we won't call it as a complete binary tree. If there is no ID missing, then only we will call it as a complete binary tree. So that is the logic. So first step is, we are going to number the nodes, and second step is, we are using the BFS traversal. So we are not going to do like 2 passes on it, but we will do in a single pass basically. So that means while we do the BFS traversal, we try to number them. Okay, we try to number them. When we number them, we will have to follow this thing. If the number is I, we will be numbering the left subtree as 2 into I, numbering the right subtree as 2 into I plus 1. So that is the principle we will follow for numbering, as well as checking whether that particular number is existing and no number is missing in between. Okay, let's go ahead and jump into the code, right. So we are passed with a tree node root. So we are given with the root node of the binary tree. So for the purpose of traversing through the binary tree and numbering them, right, I have created a placeholder class called node. Okay, so which will have a pointer to the tree node and an ID. So this is what I was calling numbering the binary tree nodes, right. So this ID will contain the number. Okay, so this is different from the value which is inside the tree node. Okay, so this node has a pointer to the tree node and its number. Okay, so that is what the placeholder for us. So let's go back to the original code. So if the root itself is null, we will say okay, null tree is already a complete binary tree. That's why we will say true. And next we will initialize a queue. Okay, and we will put the root node with the number 1. As we said, root node is numbered as 1, right? And we will initialize an ID to 1. So this will be used to check. So this is a cross verification. Okay, So this will be used for cross verification. If there is any ID missing, then we would say immediately, okay, this is not a complete binary tree. Okay. So now, so we added the root node into the queue, and we will go through this while loop as long as the queue has at least one element, right? While the queue count is not equal to 0, we will enter. So get the node from queue. So we know that queue is a first in first out data structure, right? So whatever the elements that we have inserted first, that will be also taken out first, right? So we have taken out the first element, and if that's ID, whatever the ID is same as this ID, the cross verification ID, then we are good. If it is not, then we would return false, right? And if it is same, that means we will have to increment the ID. That means whatever the next ID that we are going to insert into the queue will be this reflected one. Now, if the current nodes tree node pointer is there, right? Tn is tree node pointer. If it has left subtree, that means we are going to insert the left subtree into left subtree node to queue. What is the ID for that? You will multiply with the current ID by 2 because it is a left subtree, right? And for the right subtree, you multiply the current ID with 2 and add 1. So that is the ID for right subtree. So likewise, we will be proceeding further. So this while loop gets executed as long as there are some nodes in the given binary tree, right? So if at all the ID doesn't matches whatever the cross verification ID, right, we will return false. Otherwise, at the end of the while loop, that means we have traversed through the entire node set in the binary tree, and we did not miss any IDs here. We did not miss any IDs. Then we will return true. So that is how this code works, right? If you look at the explanation, right, the written things here, it just exactly follows the code, whatever we have exactly follows the description. Okay. So let's go ahead and look at the time complexity and space complexity, right? Time and space. Good. So time complexity. So time complexity will be how many times we are revisiting all the nodes. So let's say we have n nodes in the binary tree. N nodes in binary tree. So then we will say order of n. Okay, order of n is the time complexity because we are visiting each node exactly once, right? So order of n is the nodes. So n is the nodes and order of n is the time complexity. Let's look at the space. So for space, we are using a queue, right? So the node will have a pointer to the tree node and an ID, right? So the node structure is a pointer to tree node and an ID. So how many entries will be there in a given at a given time in the queue? It will be almost equal to the level h, right? So if the tree has h levels, right, the maximum number of nodes in the queue at a given time will be order of 2 power h, right? 2 power h. If there are h, let's say h is the last level, h is the last level, right? H is the last level, let's say, right? Then we will have order of 2 power h nodes. That is a requirement for queue, right? If the level is 3, right, we will store a maximum of 8 nodes in the queue. Remember, the queue is not keeping all of the nodes that we are visiting in the binary tree at one time, right? So the nodes are coming and going into the queue, right? So nodes are coming and going into the queue. So the 2 power h will be lot less than n, right? So if there are let's say this example, right, if there are 7 nodes, so the maximum number of nodes in the level 2 are 4. So at the maximum, the queue will have 2 power h, that means 2 power 2, right? 4 nodes, right? Even though the number of nodes in the tree are 7, the nodes which we will be putting into the queue are lesser than order of n. So even though the number 2 power h looks larger, but it is actually much smaller than n. If n is 100, let's say, right, that means there are 100 nodes in the binary tree, right? So that means, so we can just do a simple calculation of how many nodes in each level, right? First level, that means 0th level, it will be 1. Second level, first level, it will be 2, 4, right, 8 and 16, right, 16, 32, 64, right? So by now we have reached almost 99, 95 nodes, right? 99 nodes basically, or even more. So the maximum you could, if there are 100 nodes, right, the maximum in the queue will be 64 nodes. So that's the 2 power h concept. So 2 power h is the space complexity that we need, where h is the highest level. So time complexity is order of n, space complexity is order of 2 power h. If you have any questions, please post them in the comment section below this video. I will get back to you as soon as I can. I have posted this code to the GitHub repository. You can find the link below the description below in this video. If you haven't subscribed to my channel yet, please go ahead and subscribe. Also share among your friends. Please click on the bell icon while you subscribe so that you will get notifications about my future videos. Thank you for watching. I will be back with another problem from Leetcode soon. Till then, stay safe. Goodbye.